Assalamualaikum and good day everyone. So as for today we are going to continue on the last part of our design of pre-stressed concrete beam under the ultimate limit state, right? So we are going to go into the shear resistance, right? So previously in the previous lecture we have already covered on the ultimate moment of resistance, considering the flexural resistance of the beam, right? So as for today, right, we are going to cover on the shear resistance, right? So first we will look into the lesson outcomes, of this topic, right? So at the end of this lesson, you should be able to check the shear resistance of the beam considering the effect of pre-stress, and the second one is to propose the suitable shear reinforcement for the design beam. Right? So basically we are going to learn how to design the shear links. Right? Okay, so now we go to the introduction of this topic. Right? So what we are considering here is the shear behavior of our beam. Right? So the shear behavior or the shear resistance is considered at the ultimate limit state. Meaning to say that we are going to consider all the partial factor of safety in our section. Right? So the design for shear involves the most severe loading conditions, right? Considering the partial factor of safety for actions at ULS. Right, so it is the response of a member resisting shear it is similar to the reinforced concrete, right? So as you can see here in the figures that we have here, right? So we can see that we have the type of cracks that will occur when it is subjected to the shear failure, right? So you can see here these are the examples, right? So we have vertical flexural crack, right? So when we talk about flexural cracks, the flexural cracks is usually vertical, right? So you can see that as for this region, which is at the bottom here, these are known as the flexural cracks. But when we are referring to the shear cracks, we are going to have inclined cracks, right? So these are the cracks that is due to the shear, right? So we can see that we are going to usually have this angle of the cracks happening in our section, right? So basically the shear failure will be of this angle, right, which is typically 45 degrees, right? So this is the loading, right, which usually occurs in our beam, which is acting from the top to bottom, and we are going to see that we are going to experience this shear failure which is near to the support, right? So this is where we usually have the maximum shear happening, right? So what we are going to do here in the design of shear reinforcement is that we are going to design for this, which are the stirrups. And as for your syllabus, we are going to cover only vertical stirrups, and you can see that these stirrups are arranged in this direction, which is to resist the failure that might be happening within this range, right? So you can see here this is the expected shear crack, which is an inclined crack, right? And we are going to provide this vertical shear links, vertical links, in order to um, resist this failure, right? So it is in the almost perpendicular direction to the shear failure, expected shear failure, right? So these are the shear failure that we are going to cater in this topic. Right, so the additional effects of the compression due to the pre-stressing force will be considered in the design of pre-stressed concrete beam, right? So we know that previously it has been stated here that the behavior of the shear behavior is similar to reinforced concrete. Only that we are going to consider another factor, which is the additional effect, right? So this additional effect will be due to the arrangement of our tendons in our pre-stressed concrete beam, right? So this additional effect will increase the shear resistance. So as for the design of shear, it will enhance or it will add up to the value of the shear capacity, which is the value we are DC. Right, so this value VRDC is going to be using the similar equation, okay, as what we have used previously in the reinforced concrete design. Right, okay, so we are going to learn back, okay, on how to calculate these values, okay, and we are going to add up with this additional effect. Right, okay, so in the design of shear force, okay, it is permissible to consider the vertical component of force, right, in any inclined tendons acting in the direction that resists shear. Right, so this additional component, okay, that we are going to consider, okay, in the design of shear force for a pressurized concrete beam, okay, is only if we have an inclined tendon. Okay, so why is that? Okay, it is due to the location of the tendons itself, okay, which will be in the direction that is opposite, okay, to the direction of cracks in our section. Right, so thus, okay, it will enhance the shear capacity of the section. Right, so you can see here, say for example, if we are having an inclined tendon, okay, here, okay, so we can see that this tendon, okay, is acting in the uh, direction, okay, that is opposite, okay, to the direction of shear. So this more or less, okay, could help to cater for the shear resistance. Okay, so that is why we are going to have that additional component. Okay, right, so here we are going to consider, okay, the vertical component, okay, due to this inclined tendon. So later in the example, okay, we are going to see how to calculate that vertical component of force, right, which is also known as VT. Right, okay, so next, so as for the design of a shear reinforcement, okay, we are going to have three conditions, okay, that can be considered. Right, so the first one, okay, is sections that does not require design shear reinforcement. Right, so the basis of the design of shear reinforcement is basically similar to the RC design. Right, so even in RC design also we have sections that does not require any shear reinforcements. So similarly for a pressurized concrete design, right? So this occurs, okay, for sections that does not require design shear reinforcement. It occurs in regions in PFC beams, okay, where shear forces are small, right? Okay, if we have very small shear forces, okay, that is acting on our beam, okay, therefore usually we do not require any shear reinforcements. And considering additional effects of forces attributed by the inclined pre-stressing tendon. Right, so this is what I've mentioned previously. So the concrete have sufficient shear capacity, okay, VRDC, to resist the ultimate shear force, okay, which is VED. So VED is calculated based on our loading for our section. Right, so we have this as the design shear force. Right, so for this case, okay, where the section does not require design shear reinforcement, we are going to have, okay, our VRDC value, okay, is larger than the VED value. Right, okay, so we have a wrong sign here. Right, so it is supposed to be like this. Right, okay, so this VRDC, okay, is the shear resistance of our section itself. Okay, and while this VED is due to the subjected loadings. Right, so when we have this VRDC, or the shear resistance of our section, is larger than the subjected shear, right, so therefore we can consider that the concrete already have sufficient shear capacity. Right, so I just write it here. Right, so we are going to have VED, okay, which is due to the subjected shear, okay, is lesser or equal to VRDC. Right, so this is the condition. Right, so provide minimum amount of shear links, okay, except for minor members, okay, for short span or lightly loaded lintel. Right, so as for these sections that does not require design shear reinforcement, you can refer to the Eurocode 2, okay, clause 6.2.2. Right, so if we want to check for the exact clause. Right, so we are going to provide, when we are talking about beams, okay, we are going to provide links, okay, however it is only minimum links. Okay, right, so you can see here, this is the clause, okay, that we are referring to. Right, so if we read it up, right? So in regions where of the members, okay, where VED is lesser or equal to VRDC, therefore no calculated shear reinforcement is necessary. Okay, whereas VED is the design shear force in the section considered resulting from external loading and pre-stressing, right? So bonded or unbonded, right? So when on the basis of a design shear calculation, no shear reinforcement is required, minimum shear reinforcement should nevertheless be provided, right? So this is the statement, right? So even though, okay, we have decided that no shear reinforcement is required, however, we are going to apply, okay, some minimum shear reinforcements, right? So we are going to still provide the links, okay, however, okay, the calculation for that provided link will be minimum, right? Okay, so the minimum shear reinforcement may be omitted, right? So we can uh, uh, omit, right? So we can does not provide, okay, this links if we have members such as slabs, right? So solid rib slab or hollow core slab where transverse redistribution of loads is possible, right? So if you still remember in the design of a reinforced concrete slab, we do not provide any shear links. Okay, so why is that? Okay, it is because the shear values are very small, okay, and it can be distributed all over the slab, right? Then minimum reinforcement may also be omitted, okay, in members of minor importance. For example, lintels with span less than 2 meters, which do not contribute significantly to the overall resistance and stability of the structure, right? So when we talk about members that does not actually contribute as one of the structural members, okay, for example, this lintel, right? So we know that, okay, this lintel, okay, is actually just meant to cater for the loading, okay, from the brickworks, okay, that is on top of the opening, right? So it is on top of windows or it is on top of doors, right? So these are lintels, right? So for this type of element, right? So the shear links can be the shear links or the links can be omitted, right? So we can just simply provide only a longitudinal reinforcement, right? So we do not need to provide any shear links, right? Okay, so these are the cases. Okay, so we have slabs or we also have lintels. Okay, but when we talk about beams, okay, which is usually the main element, okay, for our section, right? So therefore we are required to provide at least minimum shear reinforcement, okay, right? So later we are going to go through the examples, okay, the flow, right? Okay, whereas we can see the difference, okay, between the equations, okay, for members that is requiring the shear reinforcement and also for the minimum shear reinforcement, okay, right? So for sections that does not require design shear reinforcement, so these are the equations, right? So this equation of VRDC, okay, is the shear resistance of the members equation, right? So we have VRDC equals to 0.12 K times with 100 rho L KFCK to the power of 1 over 3, right? So if you still remember in the design of reinforced concrete, right? So we are using this um, portion of the equation. Okay, so as for the design of a pre-stressed concrete beam, we have this additional term, right? So this additional term is due to the pre-stress. Okay, whereas we have the effect of pre-stress enhancing the shear capacity of the section, okay, by 15% of the longitudinal stress due to pre-stressing, right? So this is the first one, okay, whereas we are going to consider this 15% contribution, right? Okay, so we have here, okay, we are going to add up, okay, this equation, okay, with this portion, right? So we have 0.15 times with sigma CP, okay, which is the sigma CP is the actual stress in the section due to pre-stress, and in the Eurocode, okay, it has been stated like this, okay, as this term. Okay, whereas we have NED divided by AC. So AC is the area of our section, right? So it can be calculated, okay, using this equation, okay, whereas we are going to consider the partial factor of safety for the pre-stress force, then multiply with the pre-stress loss, okay, and multiply with the initial pre-stress force, right? Okay, so as for our value, right, so we need to consider these factors as well. Then divide this by the area, okay, and these values are limited by this, okay, which is 0.2 times with FCD, right? So as for the value, okay, here, okay, we are required to do the comparison, okay, between the value that we have calculated, which is NED over AC, okay, and the value has to be less than 0.133 FCK, right? Okay, so this will be the value for the sigma CP, right? Okay, so you are going to be required to calculate this first, okay, and also do a comparison, okay, with this 0.133 FCK. So this is the requirement, right? So we are not the value, okay, should not be larger than 0.133 FCK. Alright, okay. So as for this FCD, right, so this FCD is actually the value of the design strength, right? So you will have to divide, okay, the design the FCK value, the characteristic strength, okay, by the partial factor of safety for material, okay, which is for concrete in particular, for as for this section, right? Okay, so then as for this VRDC value, right, so it is also limited, okay, to this equation, okay, whereas we have the minimum value of VRDC, right? So once you calculate this VRDC, okay, you have to compare with this minimum value. So if the value is smaller, okay, than the minimum value, so therefore, okay, the value that we are going to consider for our section will be this second equation, right? Okay, so you can see that the equation is almost the same, okay, only that we have this difference in the first term, right? Okay, so this is actually similar to the reinforced concrete design, right? Okay, whereas we are going to compare these two values as well. Okay, and in the equation also we have the term K, okay, and also we have rho L, right? So as for the term K, we can calculate using this, and it is limited to 2, right? So the value should not be more than 2, right? Then as for rho L, right, so this is ASL divided by BWD, okay, whereas ASL, okay, is the area of tensile reinforcement that extends beyond the section being considered by at least a full encouraged length, okay, plus with one effective depth D, right? Okay, so as for this, okay, we can refer to this figure, right? Okay, whereas we are going to consider this ASL value, right? So this ASL value, okay, we are going to look into, okay, the value, the reinforcement, okay, that is extended beyond the section considered, right? So if we are going to consider our VED, okay, or our shear to be at this location, right? So therefore we are going to consider the reinforcement that is extended towards that location, right? So that would be the ASL that is to be substituted into the previous equation, right? Okay, and this rho L value is also limited to 0.02, right? So the value should not be more than this, right? Okay, and then we have BW, right? So BW is the smallest width of the section, right? So just in case we have flat sections, okay, so therefore we need to use the web thickness, okay, instead of the flash thickness, okay, right? So next, so this is the FOS value, which is the partial factor of safety, right? Okay, so for concrete, okay, when we are using this for the FCD equation, right? So if we are calculating for FCD, so the equation is actually FCK divided by 1.5, right? Okay, which is this one, considering the partial factor of safety for concrete, right? Okay, so we are going to use this. So this will be the FCD value. Okay, right. So that is the first condition. This is the second condition, okay, that we can consider. okay, which is the shear strength without shear reinforcement, okay, where we have regions of uncrack in bending, right? So this is considered as a special case, right? So this is the case, okay, of a single span beam, right? So in regions which are uncracked in bending, right? That is where sagging moments are relatively small near the supports, right? So this is where we are considering this. Okay, so the shear strength of the concrete section could be governed by the development of excessive tensile stresses in the concrete. So the flexural tensile stress Ft in the uncracked section does not exceed FCTK over gamma C, right? Okay, whereas the FCTK is the characteristic axial tensile strength of the concrete. So this is a special case, okay, that need to be considered, right? So when we are considering this special case, right, so we are actually going to consider the shear stress in the section, right? So if you still remember in the your solid mechanics, right? So you have already learned on this, right? Whereas we can calculate the shear stress in our section. So what is the maximum shear stress in our section, right? So the calculation is basically based on this, right? So the design equation, okay, that is given in the Eurocode, okay, is expressed by this, right? Whereas we have another equation of VRDC. So previously we have already go through two equations, okay, whereas we have on this one, right? So if we go back, right, so we have just now we have these two equations. So this is the first one, then this is the second one, okay, which we have to check, okay, then this is the third one, right? So this third equation is considering the special case, right? Okay, whereas in this equation we have BW, we have I, okay, then we have E Y bar, right? So Y bar is the distance, okay, between the our section, okay, to the centroid, right? Okay, so you can see here, okay, we also have FCTD, right? Okay, which we can calculate, okay, based on the FCTK value, okay, and also we have the alpha value, right? So this alpha value, okay, will be taken as 1, okay, for post tension tendons, okay, and less than 1 for pretension tendons, right? So this value of alpha 1, okay, is given in the Eurocode, okay, in accordance to the distance of section being considered, right? Okay, so this is the equation, okay, that we are going to use, which is another equation of VRDC. And in a reinforced concrete, in a section, okay, it is actually hard to exactly determine the location of the uncracked section at UFS. So therefore, both equations needs to be calculated, right? So just now we have one equation, two equations for VRDC that is calculated for sections with no shear reinforcements, okay. Then we also check that value of VRDC, okay, with the value of VRDC for this uncracked section, right? So we are going to compare those values, okay, and we are going to do a selection of value, which is the lowest value, right? So the lowest value of VRDC will be taken as the shear capacity of the section, right? So that will be used, okay, in order to proceed, okay, with the design of shear reinforcement, okay. Right, so then another one, okay, is another condition, right? So this is the third condition where we have sections that require design shear reinforcement, right? So as for this, you can refer to the Eurocode 2 clause 6.2.3, right? So the method that is used, okay, for this design of shear reinforcement is the variable strut inclination method, right? So it is identical to RC design, okay, whereas we are going to compare our VED value with the VRD max value, right? So this is the equation that we are going to apply, right? Whereas this equation is actually similar to the equation that we have used before, right? Okay, only that now, okay, we are going to consider, okay, the value, okay, of sigma CP, right? Okay, as the value that we have used previously, okay, whereas we are going to consider the stress, okay, that is due to the pre-stressing force, right? Okay, so this is the equation. So VRD max is equals to alpha CW, right? So this alpha CW, okay, will be based on this these conditions, right? Okay, so we have the comparison, okay, between FCK values, right? So we need to calculate this first, okay, in order to determine, okay, in which range, okay, this our value of sigma CP is placed on. Alright, okay, so therefore from there we can determine the alpha CW value, right? So then we also have BW, okay, which is the web width, okay, then we have Z, alright? So in a pre-stressed concrete section, we are considering Z equals to 0.9 D, right? Then V1, right, so we have this equation which is 0.6, okay, times with 1 minus with FCK over 250, right, okay, and divided by 1.5 cotangent theta plus with tangent theta, right? Okay, so the VRD max value, okay, when we already substituted those values of V1 and also Z, right, so we can see that we have this as the complete equation, right? So this will be the equation of VRD max. Okay, right. So this VRD max, okay, since in the equation we have this theta value, right? So we know that in the design of shear reinforcements, okay, we are going to limit the values of theta, okay, to be in between 22 degrees to 45 degrees, right? So therefore, okay, we are going, if we are substituting the values of the theta, okay, into the equation, so we are going to have these two equations. So one is for 22 degrees and another one is for 45 degrees. Okay, and if the value of the VED, okay, is larger than the VRD max value that is due to 22 degrees, right? So therefore we can recalculate, okay, the value of theta using this equation, right? So later I will show you, okay, in the flow chart, okay, on where to calculate this theta value, okay. Right, so then in a pre-tension, in a post-tension section, okay, we also have the consideration of ducts, right? So if web section contains grouted ducts, okay, with the diameter of more than 1/8 of the web thickness, right? So therefore the web thickness should be reduced by 1.5 of the sum of the duct diameters measured. Right, okay, so we are going to consider the on reducing the web thickness, right? Because when we talk about a large grouted ducts, right? So therefore we are going to have the effect, okay, of the area reduction, okay, of the web thickness, right? So that is why we have this reduction of the web thickness, right? Then for non-grouted ducts, okay, grouted plastic ducts or unbonded tendons, right? So the web thickness should be reduced by 1.2, right? So, okay, so that is all. That is for if we are providing ducts in our section, right? Okay, then another equation, right? Another step is on the vertical shear reinforcement. So shear reinforcement has to be provided to resist shear force if it cannot be sustained by the concrete section, including enhanced shear resistance due to the effect of pre-stress, right? So you can see here that we have two equations, okay? One is equation that is for the shear reinforcement itself, right? So this is for the shear reinforcement, okay? And another one here is for the minimum shear reinforcement, right? So this is the minimum shear reinforcement that has to be provided just in case we do not require any shear reinforcements, okay, right? So these two equations, okay, looks almost the same, okay, only that, okay, we are going to have a smaller value, okay, for the ASW minimum, right? Okay, so what we are achieving here are the values of ASW over S, right? So for the limiting values of cotangent theta, right, so if we are rearranging the equation, then we are going to have these two equations, right? So however, you can just simply substitute the value of cotangent theta into this equation, right? So for cotangent for 22 degrees, right? So if we are considering the uh, angle to be 22 degrees, so therefore cotangent theta will be 2.5, and when we are considering this 45 degrees, therefore the cotangent theta will be a 1, right? So you can just substitute into the equation to get this complete equation of the shear reinforcement design, right? Okay, then we also have additional longitudinal force. Okay, so when using this method for design, it is necessary to provide reinforcement for the tensile force generated in the tension cord of the assumed truss. So for vertical links, okay, the tensile force FTD to be provided in the tensile zone, right? Okay, so you can calculate this value of the tensile force using this equation, right? So this is one additional one which is not in the RC design, right? So we have FTD equals to 0.87 FYKASL, right? So this untensioned reinforcement of area ASL must be provided to ensure the force is developed. So the profile of the pre-stressing tendons may be adjusted to provide greater resistance to the design shear force if required. Okay, right. So this is the flow. Okay, so this is the overall flow. Okay, actually for the design of shear reinforcement. Right, so you can see that we have this first part. Okay, and it will bring you up to the additional longitudinal force caused by the shear that is discussed previously in the previous slide. Right, so you can see here that we are going to start with the comparison between VED with VRDC, right? So what you have to do first in the shear reinforcement design procedure is that you need to calculate VED and also you need to calculate VRDC first, right? Then you are going to make a comparison between these two values, which are VED and also VRDC. So if VED is larger than VRDC, therefore we are going to follow the left flow. However, if VED is less or equal to VRDC, therefore we are going to consider the second flow, right? Whereas here we have VED is less or equal to VRDC. So if you still remember, this is the condition where shear reinforcement is not required. Right. So shear reinforcement is not required. So therefore provide minimum reinforcement. So instead of having to calculate all the values of VRD max and so on, right? So if this is the case where VED is less or equal to VRDC, therefore you can go straight to the design of minimum reinforcement, right? So we are going to use this equation of ASW over S equals to 0.08 PW square root FCK over FYK, right? So straightforward, we are going to get the reinforcement. Then you can proceed to the additional longitudinal force calculated caused by the shear, right? So we can calculate this straightforward, right? But if we have our value VED is larger than VRDC, therefore we know that the shear reinforcement is required. So we are going to go to the left flow, right? So if VED is larger than VRDC, so we know that shear reinforcement is required. So therefore we need to calculate another value. So using the same VED value, we are going to calculate the VRD max to be compared with that VED. Alright, so this VRD max will be using the equation that we have used previously with the value of cotangent theta. Right, and the first theta value that we are going to use here is the value of 22 degrees, right? So we start with 22 degrees first. Then only we are going to proceed with 45 degrees if required. So we are going to calculate VRD max using the theta value of 22 degrees. Then if the value of VED is less or equals to VRD max, therefore we are going to design the shear reinforcement, right? So design shear reinforcement using this equation. So this is the equation for shear reinforcement. Right, so we are going to calculate using ASW over S, K equals to this equation, and this theta value that we are going to apply here is 22 degrees, right? Okay, because it fulfills, okay, the requirement of this VRD max, right? So from here, okay, then we can proceed to the calculation of the additional longitudinal force, right? But if for this section, okay, we have VED is larger than VRD max, right? So if we have this condition, whereas VED is larger than VRD max at 22 degrees. So therefore, we are going to follow this flow. Okay, whereas we are going to recalculate this value of VRD max. And now we are going to consider the value at 45 degrees theta. Right. So here, we are going to recalculate the value of VRD max using theta 45 degrees, and we are going to compare back with VED. Right. So this VED value is the same value that we have used here. Right, so we are going to compare back VED with VRD max. So if VED is lesser or equal to VRD max in this part, right, therefore we are going to recalculate the value of theta to be used in the equation of the design of the shear reinforcement design, right? So we are going to recalculate this value theta, and this theta value will be substituted into the equation ASW over S, right? So you can see here, instead of using this 22 degrees, right, we are going to use the value theta that has been calculated here, right? So this theta will be substituted into this equation. If that is the case, whereas we have VED is less or equal to VRD max with the theta value of 45 degrees, right? Okay, so here, this is the new theta. So this new theta will be used in this shear reinforcement calculation. Okay, so that is one condition. Then this is another condition, okay, whereas we have VED is larger than VRD max. So if VED is larger than VRD max with theta value 45 degrees, therefore we are going to follow this flow, right? So as for this, okay, we are going to increase, okay, the size of the beam or use higher concrete class, which means, okay, that we have to redesign back our section, right? So you can see here, this is the overall view, okay, of the shear reinforcement design procedure, right? So we will start with the comparison with VRDC. Okay, then we are going to decide, okay, whether the shear reinforcement is required or not. Okay, then we will proceed to the design of the shear reinforcements. Okay, right? So this is the overall view, right? So later when we do the example, okay, then you can see, okay, that we are going to follow this flow. Okay, and from this flow, we can see which equation that we are going to require. Okay, right. And these are the equations, okay, that we are going to use, right? So we have VED, okay, and also we have VEF, right? So usually this maximum shear force is considered at the face of the support, right? So however, in the design of predominantly UDL, okay, whereas we have a normal UDL on our beam, right? VED can be calculated at a distance D, okay, from the face of the support, right? So shear reinforcement should be provided to the face of the support, okay, right? So you can see here, okay, that this is the location, okay, whereas we are going to calculate, okay, and use the value of our VED value, right? Okay, so usually we are going to consider that distance of D, right? Okay, then we have the equations, right? So these are the equations that has been mentioned, okay, in the flow chart, right? So we have VRDC in this part A. Okay, then we also have this equation for part B, okay, which is for VRD max, right? So VRDC, you can see that we have these two equations. So you need two equations for VRDC. This first VRDC, okay, then considering the pre-stress force, okay, so therefore we are going to have the second VRDC that is for the uncracked section, right? So you need to calculate all these three VRDC's values, okay, and you are going to choose, okay, the lesser value, okay, in order to be compared with our VED, right? So that is for VRDC. Okay, then we also have VRD max, okay, whereas we have this cotangent theta, right? So we have this theta value. So just now, okay, we have already discussed on whereas we have the two values, two different values of theta. So we will start with 22 degrees. Okay, then if the value of VED is larger than VRD max, therefore we are going to recalculate the value of VRD max, okay, using the theta value of 45 degrees as well, right? Okay, so these are only the equations that we are going to apply, okay, together with the flowchart. Okay, right.